Hello, this is Chapter 15, Notes 2 on Thermodynamics, and I have a worked problem from WebAssign. So we have this worked problem from WebAssign 2. Why? Well, last night I made an executive decision to shut down WebAssign 2, and I closed it out. And I decided to go over the problem, the second problem that is, in a video, which is this one. And then I reassigned it. So it's now due Wednesday. So there's good news and bad news. The bad news, since I'm redoing it, I decided to double the points for the second problem. So now instead of the second problem being worth, I think it was 6 points, it's now worth 12 points. The good news, the people who already had 100%, who already did it and did it all correctly, you guys just got 2 bonus points. And some more good news. The folks who already did it and did it pretty good, they had like an 87% I think on it, they just got 1 bonus point. You can go back in and try and get 100 and you'll keep that bonus point. All right, let's look at the problem. So you looked at problem number 2 in this WebAssign, and 1, there's 6 parts to it. And 2, it talks about specific heat and coefficient of linear expansion and Young's modulus and stuff that either A, we haven't had, or B, we had a long time ago. So you right away say, I can't do the problem. But that's not the right way to do it. What you do is you isolate it one step at a time, looking at part A, and you go ahead and use that old guess method of writing down what you know and what you don't know. And so you put it all down, what you know and what you're hunting for, and you get these distance and mass and delta T, and you're hunting for Q, and you got the C. That should ring a bell for you. Granted, it was way back in Chapter 13, but it should still ring a bell. And if you have to, go back to Chapter 13 and find that formula. And that formula was fairly straightforward. Q equals MC delta T. And you got all that stuff, so it becomes sort of a plug and chug, and you get an answer. The difficulty with the answer is if you're careful with your units, the answer that you just got is in kilocalories, and the units in the answer blank are joules. So you got to convert. Always have to watch those units. And then you get the right answer, 1.99 times 10 to the 8th joules for those particular numbers. Of course, every student has different numbers. So that's part A. It wasn't too bad. Just required you to go back in time to Chapter 13 and then to reconsider units. Next one is part B. What is its change in length if the coefficient of linear expansion is 2.5 times 10 to the negative 6 per degree centigrade? Celsius. One of those two. So, change in length, coefficient of linear expansion. Wow, that sounds like past stuff again. Once again, you're going to have to look back in what you've already learned. And again, write down what you know, and then just go back and find that formula. Coefficient of linear expansion, I forgot that the symbol was an alpha, but I went back and looked and found it and found the formula. And we've got that. Length, change in length, we've got the original length, 7.5 meters, got it written down over here. Delta T, we've got a delta T. Once again, it becomes pretty much a plug and chug, making sure our units were all okay, and they were this time. The change in length is pretty small, 10 to the minus 4th meters, but it's there. There is indeed a change in length. So we got that one done. Moving on to part C. Part C has this Young's modulus. Now, it's tempting to say, well, we got an area, we got, meters squared, we got n over meters squared. Maybe I could just use some dimensional analysis and just multiply them and get the force. And while it's tempting, it doesn't work that way. So there's a couple of ways to do this. You can look up Young's modulus on the internet, or, they're talking about expansion and forces And it sounds like it might be like springs. So I went back and looked at chapter 5, which we haven't covered in this book, but it talks about Young's modulus there. One way or the other, you got to try and find out what the formula is for Young's modulus. And in chapter 5, if you look back in the book, it says tensile strength, that makes sense. Elastic modulus, or Young's modulus. And it's got delta L as a change in length, which we've already figured out. F is the applied force. Y is this factor, which we've got. A is the cross-sectional area, which you've got. And L naught is the original length. So we're looking pretty good. So let's get rid of all this other stuff. We're hunting for the force if the distance was restricted to 0 meters. If it was not allowed to change its length, like we figured out in part B. We've got the area, we've got the Young's modulus, and we've got this lovely equation because we had to hunt for it. We hadn't learned it, but we had to hunt for it. And so then the delta L is from before, from what we already solved, part B. 1 over Young's modulus, the force over the area, and then the original length, which is, again, that distance or how big the column was to begin with. And then it really is just pretty much a plug and chug, arrange some algebra, and we get the force is 1.24 times 10 to the 6 newtons, which is a fairly large force. So this one, yeah, you hadn't had Young's modulus before. You had to actually go around and hunt for it. Once you hunted for it, it wasn't too tough. So let's go on to D. How much work does it perform, the column, when it expands if it supports a mass of 1 times 10 to the 4th kilograms? Now I'm hunting for work here, and it says when it does expand. Part C was if it was not allowed to expand. So part C is not going to figure in here because here we're allowing it to expand. And then we've also got this information. It supports a mass of this. So yeah, I'm hunting for work. I got a mass. I got 2 formulas here from work. I know the old guy from last year, work equals force times distance. And I got this new and improved version of delta U, the change in internal energy, is Q minus work. Now, I'm looking back at the stuff that I've already done, and I've got a Q, but I don't have any internal energy. I've got a distance. The distances would be like how much it expands, because, that would be how it expands. So I've got this distance here. But what force would I have? Would it be this force? No, because I just said that would be if it's not allowed. So this force is out. So what force are we talking about? Well, we're talking about the force of pushing this guy up. Well, that gives us that, force of gravity. Force of gravity is equal to mass times little g. So we've got its mass times little g, and we find the force it would be pushing up on. Okay, that's the force it would have to push up with in order to support that mass. That's the distance, and we get the work done. Not a lot, only 20 joules, but still, there is work done, and that is the correct answer. So here we had 2 formulas. This guy wasn't going to cut it. This guy is the one that we're going to be using, but then the temptation is to use the force found over here in problem C. You got to understand what you did. Problem C, if it was not allowed to expand. Problem part D is when it does expand. So that force is not going to work. So you got to go back and think about last year and what force and what work is it going to be doing. And it's that force of gravity thing. Okay, let's move on to the next problem. Problem number E. What is the change in internal energy? So now we are hunting for a change in internal energy. Now we can go back and use that formula that I wanted to before of delta U equals Q minus W. because we have the work. We have the Q in joules, of course. Okay, so we're going to go ahead and got them, and we figure it out. And I'm sorry, but 1.99 times 10 to the 8th minus 20 still gives you 1.99 times 10 to the 8th. You know, those 20 joules are pretty doggone insignificant compared to what it was starting out with. So the final question is, what is the source of energy for the work performed? Oh, we could try and use all kinds of strange, bizarre things. We could talk about, you know, the building heat, people going in and out. But when you get right down to it, what the book was hunting for is the sun is shining down on it, and the source of energy is the sun. That's what caused it to heat up. And there you got it. The energy comes from the sun, heating the air in the earth, which heats the column. Those are your answers. Those are how to do them. Now you get to go back and do all that work for your particular numbers. Have fun. And that's the end of the video. Thank you for your time.